It looks like nobody will join today. Okay, we can wait 5 or 10 more minutes. Then we will start. Okay. Hmm. Please wait up to 7:30. After 4 minutes, if nobody joins, we'll start without any audience. because if nobody joins, we won't have to wait for uh, people to answer. That's why we are waiting. We will start after 1 minute or so. Yeah. So in the meantime, let me share my screen. And for the sake of recording audio, I will be commenting on the slides. So yeah. Okay, so nobody has joined. I'll not turn on my camera. So let's start. Good evening. My name is Shutunu Sadhukan. I am a chartered engineer in the Department of Chemical Engineering, and also I am a PhD student at the CRNTS, that is Center of Research in Nanotechnology and Science of IIT Bombay. And I am also a TA, that is teaching assistant of uh, National Program on Technical Educational Learning, that is NPTEL, under the PMRF scheme. And I welcome to the fourth interactive session, weekly interactive session for NPTEL course code AR18. The course title is Urban Utilities Planning, Water Supply, Sanitation and Drainage 2024. The course is instructed by Dr. Devapratim Pandit, who is a professor of IIT Kharagpur at the Department of Architecture and Regional Planning. Where are we? We are at the fourth week, that is 18th August. So last Thursday was our 78th Independence Day. So happy belated Independence Day to everyone. Regarding the recent murder case of a doctor at the Arjikar Medical Hospital of Kolkata, we stand together for the safety for doctors and all the healthcare professionals all over the world. So we'll maintain 2 minutes of silence in respect and the and for sympathy for the doctor who has been murdered in Arjikar Medical College of Kolkata. Okay, so let me check first the email whether it has been sent correctly. Yeah. Don't know why people have not joined. Okay, so I will continue for the sake of recording. Uh, so in the last class, we actually gone through different membrane processes characteristics according to their pore sizes, like microfiltration, ultrafiltration, nanofiltration, and reverse osmosis or RO, MF, UF, and NF and RO. And we discussed what are the different types of particles which are basically retained by these types of filtration mechanisms. Like in case of microfiltration, the bacteria and suspended solids are retained. In case of ultrafiltration, the virus, bacteria, and suspended solids are retained. Uh, Moreover, above of the ultrafiltration, in case of nanofiltration, the multivalent ions, which basically causes uh, the which causes the hardness, those are retained. And in case of reverse osmosis or RO, also the monovalent ions written, almost the distilled water comes out. So we also discussed the different ranges of pore size and the pressure that is applied for filtration through these types of through these different types of membrane modules. Okay, we also actually we promised in the last class that we will discuss a problem which is based on the demand and supply of water. There was a table given where recommended per capita water supply levels for designing scheme was given. So we were supposed to start a problem based on this table, but unfortunately what happened that one student approached me in social media saying that he has a doubt regarding one aquifer problem. The problem is based on aquifer, so he was not getting the correct answers. So I actually prepared a detailed explanation for the aquifer problem so that people get confidence, and even if the question there is some problem, people can identify that themselves, and they can accordingly they can answer, or they can be confident whether if the problem answer is not correct, either they will be if the option it is not matching with any of the options, they will be either they will be given marks, or what will happen, or they will be or everyone who will be attempting, they will be given marks. So anyone of that can be happen, but I strongly encourage for you to know the basics so that you are confident enough to answer, even if the correct answer is not given in the options. Okay, so now let's start with that problem. The above problem we will discuss at a later stage. So first I will discuss the principle of hydrostatic equilibrium of liquid. What is it? The equihydratability property of water basically. So there are three containers, and those containers are connected at their base. The containers may be of different height and different shape and size, but the projected height will be the same in the case when water will be poured inside one of the three interconnected containers. There may be more than three also. This is the principle of hydrostatic equilibrium of liquid. If water or any other liquid is poured inside one of the arms, the water will come into the other containers as they are connected at the bottom level. Then they will rise to equal level at all the three containers. Even if you pour the water in one container, and provided there is basically the top portion of the container is uh, open to the atmosphere. So after the container attains equal height, what will happen? That the hydrostatic pressure at each and every point inside the liquid will be the same at the same height. So if you take a point at h by 2 inside C, inside B, and inside A, all the three pressures at the h by 2 height inside A, B, and C will be equal. This principle is used for extracting water via artesian well. So if you see, there are different types of layers inside the earth crust. So if you see the interior core of the earth, at the outermost layer there is crust soil, which is a part of the earth crust. Inside of the earth crust there is there is mantle layer. Mantle has two parts. One is outer mantle and another one is inner mantle. And even if the inside of the mantle layer, that is at the center point of the earth, there is earth core. The earth core can also be divided into outer core and inner core. So the points we are talking about, this is situated at the earth crust level, not at the mantle or core level. Okay. So let's say at the earth crust level, there is groundwater present, and groundwater recharge if uh, if the lithographic structure of the earth is like this, then it may charge from the surface. So rainwater may come, and you can see there are different types of stratas, like impervious strata, which is not very well uh, conductor of water, but the pervious strata is permeable to water. So through the pervious strata, water will come into the ground with the help of rainfall from the surface of the ground. Okay, but through the impervious strata, water will not come. So what will happen? Between two layers, two impervious strata, or above the impervious strata, there will be storage of water. Okay, but uh, the height of the water is different in different places. So if we dig a bore from the bottom surface at the up to the pervious strata level where the water belt is stored, then what will happen? Due to this principle, hydrostatic equilibrium of water, this principle, the water will come into the surface, earth surface. In this way, if there is a rock mountain at the valley, people can get water with the help of this artesian wells. Now, this principle of hydrostatic equilibrium is also applied in many engineering cases, just like the hydraulic lifting and domestic water supply from municipal tanks. Just like the tank is situated at a particular height, and from that height, the water is basically at the starting level. First, from the water source, the water is treated and pumped to the overhead tank, and from that tank the water is supplied to the household via the tap. If the tap is open, due to again the hydrostatic equilibrium principle of water or liquid, the water will try to attain equal height in households similar to the tank level. So if the tank is above the households, above the highest households, then households will get the water. But if the tank is below the height of the highest household, then the highest levels may not get the water. Highest levels of the households may not get the water. So this is the hydrostatic equilibrium of liquid. Sometimes what happens, if the pipeline is very long, friction pressure drop also occurs, or if there is a very uh, if there is a very the pipeline is a lot of branched. Then also what happens, the due to the pressure drop, the water doesn't reach to equivalent height of the tank. But if we assume zero pressure drop through the pipeline, then the water should achieve the equal height of the tank. So this is called as the hydrostatic equilibrium principle of liquid. Then if we closely look into the structure of the artesian wells in confined aquifers versus in unconfined aquifers, then we will see that the so if the well that we have dug, that is permeable, then from the unconfined aquifer and from the confined aquifer, both the water will come inside the well. If we dig the well in such a way that there is reinforcement at this side, or maybe we have just inserted one pipe inside the strata, then what will happen? Then only from the bottom the water will enter. Okay. So now the aquifer or groundwater pocket that is situated between two confining beds or impermeable rock layer, then what will happen, the aquifer that is present in between, that is called as the confined aquifer, because it is confined between two confining beds. But if only one side, that is the lower side of the aquifer, uh, is surrounded by the confining bed, but the upper side of the aquifer is open to the atmosphere, then it is called as unconfined aquifer. Okay. So not always open to the atmosphere. The upper layer is basically not confined by any rock. It may be confined, it may be open to, or it may be confined with a permeable soil. Okay. So we'll see the structure of a confined aquifer. So there is impermeable or impervious strata below and above the aquifer in case of confined aquifers. Okay. And what happens if we have dug one pipe and water stream is coming from the cylindrical surface of the pipe or of the well? Then in case of confined aquifer, uh, what will happen? In case of confined aquifer, there will be the water that will be flowing through the surface, it will be constant, right? And so yeah, it is the case for the confined aquifer. Okay. So for the confined aquifer, if we just look at the governing equations, those are given by the Thiem's formula. So under this formula, discharge Q, that is volumetric flow rate, is given as 2 pi bkm into capital H minus small h divided by ln of capital R by small r, where km is nothing but the permeability of the aquifer material. Capital H is the maximum height of the water bed below the ground level, and small h is the small h is any height that is small, less than equals to capital H, which is basically if we just try to withdraw water through the well, there will be a cone formation. It is nothing but a hydrostatic gradient. So the water height at a particular location, at a particular small r distance from the center point of the well, if we just try to find out the cone height with the help of digging a test well, then at a distance small r from the center point of the oil, center point of the main oil, we will find the height small h, which is the height of the water cone at that particular distance small r from the center point. Okay, so this is the explanation of this formula. And now these 2 pi b km, these are all constant. ln means 2.303 log. Now in case of unconfined aquifer, where there is no impermeable strata or impervious strata present inside the aquifer, it is basically open. The governing equation that gives the discharge in case of this aquifer is something like this. It is given as q equals to pi into km. This 2b term is not there. Whole into capital H square minus small h square divided by ln of capital R by small r. If we just simplify this pi km and ln, it gives you capital K into capital H square minus small h square divided by log of capital R by small r. Okay, where this capital K is written in terms of the km, that is the permeability of the aquifer material, which is nothing but capital K is to pi into km divided by 2.303 aquifer transmission coefficient or constant. So aquifer transmission coefficient or aquifer transmission constant is a function of the permeability of the aquifer material. So the function is different in case of unconfined or confined. So in case of confined aquifer, it will be K confined equals to 2 pi b into km divided by 2.303. And in case of unconfined aquifer, K unconfined or Ku will be equals to pi into km divided by 2.30. Okay. So now we'll solve a problem based on the formula we just have learned. So consider the following diagram of a 20 centimeter diameter tube oil and observations made on the same. So you can see one tube oil, which is basically the main oil. Its diameter is 20 centimeter. That means the radius is 10 centimeter. It is drawing water from an open aquifer. We can see there is no impervious layer that is present in between. So the aquifer is basically open, right? So that's why it is uh, uncontained. Yeah, unconfined. Okay, so this aquifer is unconfined. It is not confined between two impervious layers. Only one side of the aquifer is there is one impervious layer is present. Okay. So now what are the observations? Number one is rate of pumping is given as 1.8 kiloliters per minute. That is the rate of pumping through this main oil, water coming out. Drawdown in 20 meter away test oil is given as 2 meter. Drawdown in 40 meter away test oil is given as 0.6 meter. Depth of water in the well before pumping is 60 meter. So we can assume that before the starting of pumping, the water was at a 60-meter height in the main well. After starting of pumping, beyond the zone of influence of the cone, there the water height will be 60 meter. Drawdown of the 40-meter away state well, that is the test well 2. It's it is basically the water height is the drawdown means 0.6 meter. That means water height is basically 60 minus 0.6 meter. That is 59.4 meter for test well 2. And test well 1, the drawdown is 2 meter height. That means the water height in the column based on the cone in the test well 1 is 60 minus 2 meter means 58 meter. Now based on the observations, we have to calculate the approximate radius r in meters, which is of the circle of influence. So there will be a point where the water height will be 60 meter. Beyond that point, at every place, the water height will be 60 meter. So we have to find that particular point. Okay. The distance of that point from the center point of the main well will be the capital R. That is nothing but the approximate radius of influence or radius of the circle of influence. Okay. So let us find out detailed solution for the radius of influence. If we apply Thiem's formula for unconfined aquifer, it is something like this. Discharge Q equals to capital K, which is the constant or coefficient, into capital A square minus small h square divided by log of capital R by small r. With respect to test well number 1, which is 20 meter away from the center point, discharge Q equals to K into 60 minus 58 square divided by log of capital R by 20. So here the small h is the height of water inside test well 1 and small r is the distance of the test well 1 from the center point. It is 20 meter. So if we just calculate the discharge Q with respect to the test well 1, then this will be the formula. At the capital R, which is the radius of influence, there the height of the water is 60 meter. If we can draw a hypothetical test well at the radius of influence of the cone, basically. Now, with respect to the test well 2, similarly, discharge Q will be, if we calculate the flow rate of the main well with respect to the test well 2, it will be K into 60 square minus 60 minus 0.6, that means 59.4 square, divided by the radius of influence where the water height is 60, divided by, it is the basically the minimum radius of influence, because beyond that also the water height is 60. So minimum radius from where the starting of water height 60, water height 60 is getting started, then only that place is basically your radius of influence, that distance of that point from the center point. Now at the distance of 40 from the center point, the water height inside the test well number 2 is 59.4 meter. Then equating both the above, because the water drawing, the test wells are just to test the height of the water based on the surface of the cone when we are drawing water from the main. Okay, So all the discharges will be basically the same, be it calculated based on test well 2 or be it calculated based on test well number 1. That doesn't matter. So discharge Q will be K equals to this one 60 minus 58 square divided by log R by 20 equals to this one K into 60 minus 59.4 square divided by log of R by 40. Okay. So just forget about the discharge K, cancel out K from both sides, then things become something like this. So 50 square minus 58 square becomes 236. Whole into log R plus 40 comes at the left hand side, which becomes log R minus log 40 equals to 60 square minus 59.4 square becomes 71.64, and log R by 20 comes from left to right and becomes log R minus log 20. Okay. Or 236 minus 71.64, this log R's coefficient come at the left hand side, whole into log R equals to this 236 minus log 40 comes to the right hand side and becomes positive. 236 minus into log 50 minus 71.64 into log 20, which was already present in the right hand side. We have to look here one thing, carefully observe one thing, that is the log means within the base, that is the 10 by default, and if it is written as ln, that is ln, that means the base is by default e. So while calculating r, if that is ln, then it will be 10 e to the power. If that is log, by default it will be 10 to the power. So it will be capital R equals to 10 to the power this thing. So it will be this divided by this. So 236 into log 40 minus 71.64 into log 20, it will be 284.88 divided by this thing. 236 minus 71.64 equals to 164.36. 10 to the power this one equals to 10 to the power root 3 basically. 10 to the power 1.732 equals to 54 almost, which is in meter. So 54 meter is the radius of influence we have calculated. That is the distance from the main oil. That is beyond the test well 2. You can imagine a test well 3 there. Okay. Still nobody has joined. So we will not give any break. We will just continue, and maybe today's class may get finished within 8:30 and 8:40. Let's see. So we have calculated the circle of influence, which is 54 meter. Now the second question is, we have to calculate the permeability, that is km in meter per second of the aquifer material. Welcome Dipankar. Previously basically nobody joined, so I was just continuing for the sake of recording. I will just repeat the things once again for you. One student was there who actually contacted me stating, do you want to say something? Okay. So one student was there who basically contacted me stating, yes, please. Okay. So that student, Dipankar has left. Okay. So, okay, let me continue. If he joins, I will brief him the introduction. So now detailed solution for permeability Km of the aquifer material. Let me switch off my camera. No need. Okay. So aquifer transmission coefficient for confined aquifer is given as Kc equals to 2 pi b into Km divided by 2.303 that we have seen earlier. Now aquifer transmission coefficient or constant for unconfined aquifer is given as K u or K equals to simply pi into Km divided by 2.303. So basically Ku into 2b equals to Kc or Kc equals to 2b into Ku. This also you can infer from these two formulas. Right. Or simply K. Kc equals to 2 pi K, 2bk. Yeah. So now applying Thiem's formula to test oil number 1, you can apply that to test oil 2 also. Or you can apply that even at the radius of influence also. If you apply it to test oil 1, then discharge Q becomes 1.8 kiloliter per minute, which is nothing but 1800 liters per minute, right? Which is nothing but equals to, based on the formula, capital K into capital I square minus small I square divided by log of capital R by small r. Now we have converted liter per minute to liter per second. That means 30 liter per second equals to K into capital H. In the place of capital H, we can put the value that is the maximum value, which is nothing but 60. If we are putting it as 60, then we have to put capital R as the radius of influential circle, which is nothing but 54. And if we are taking small h, that is the test well 1, then we have to take small r, it is the distance from the center point and the test well. It will be 20 meters. So smaller is 20. So if you solve that, it will become capital A into 60 square means 3600 minus 50 square means 3364. It will be meter squared because 60 and 50 both are meters, divided by log of meter by meter gets cancelled out, 27 by 10, because 54 by 20 after simplification it came something like this. Then if we convert liter per second into meter cube per second, liter means what? Kilo hecto decameter deci. So 1 cubic decimeter means 1 liter. That's why 1 meter cube equals to 1000 cubic decimeter. That means 1000 liters. So 1 meter cube equals to 1000 liter. So to convert liter per second into meter cube per second, we have to divide by 1000. Simple. Then this becomes equals to 60 square minus 58 square, that is 236 meter square whole into K divided by log of 2.7, which becomes K into 236 by log of 2.7 becomes 547.102 meter square. Hence, aquifer transmission coefficient K is nothing but 0.03 divided by 547.102, which is nothing but 54.835 micrometer per second. Okay, micro means 54.85 into 10 to the power minus 6 meter per second. This unit will be meter per second because meter square and meter cube gets cancelled, becomes meter per second. Okay, so 54.834 into 10 to the power minus 6 meter per second. That means micrometer per second. Then from the aquifer transmission coefficient of unconfined aquifer, we can get the value of the permeability of aquifer material, that is, which is nothing but small km. This small km becomes 2.303 into capital K divided by pi in case of unconfined aquifer, which is nothing but 54.834 into 2.303 divided by pi equals to 40.2 micrometer per second. Units remains the same for pi and for This 2.0, it has no units, so units remain the same. Hope it is well understandable. Then comes the we have calculated the permeability in this way, which is nothing but 40.2 meter per second for the aquifer material. Now the third question is, based on whatever we have calculated till now, we have to calculate the maximum rate, that is QM of volumetric discharge of the oil. Okay, so what will be the maximum rate? So as we gradually withdraw water, the rate will be decreased, right? But when the rate was 60 meter, 60-meter height is where it is at the R, capital R, which is nothing but your radius of influence. There, the rate will be the maximum. Based on that, we will now go through the detailed solution for maximum discharge rate of the oil. So to calculate that, first we will again revise whatever the data are given. Capital H is given as 60 meter, which is the radius of influence, that is capital R. At the radius of influence, the height is capital H, which is nothing but is 60 meter. Small h is 0 meter for maximum discharge of the oil. Because we are calculating the maximum discharge, we are not calculating the high water, where the discharge is maximum at that moment of time, the small h will be 0. Okay. So the cone is actually not shown very well here. So it will be something like this. It will be a slopey nature. So again, we can go back to the earlier picture. Yeah. So again, it is something like at the radius small r, which is zero point 0.1 in our case. At 0.1 distance and below also, from 0 to 0.1, around the center point of the main oil, the height of the water will be basically almost 0 for maximum discharge. So it is kind of slope kind of thing will be there. Okay. It is not a straight line as it is shown. So at that particular height, what will happen? We are coming into that. Yeah. So 0 meter. So small h will be 0 meter if we are withdrawing water at a maximum. Now smaller will be, as I told, it is 10 centimeter. That means 0.1 millimeter. Sorry, 0.1 meter. That is the radius of the principal well. So there is one problem here. It will not be 10 centimeter. It will be, no, 10 centimeter means 100. Yes, it's 0.1 meter. Yeah, yeah. It is correct. No issues with that. So data obtained that we obtained in our previous during solving our previous two problems. It is capital R, which is the radius of influence at capital H, height of the water. It will be at y direction is capital H. Then the x direction becomes, radial direction becomes 54.11 meter, which is nothing but the radius of influence. Now capital K, which is the AT coefficient, that is aquifer transmittance coefficient or aquifer transmittance constant. It is 54.83 micrometer per second that we have calculated earlier. Now, based on these two things, the data given and data obtained, we are going to apply the Thiem's formula for volumetric flow rate. So, for maximum discharge QM, K into capital A square minus small a square into log capital R by small r will be K capital A square divided by log capital R by small r, because small h is 0 here for maximum discharge of the oil. So, it becomes 0. K squared by log r by r. It is becomes the expression of the QM. Upon simplification, we just put the values of K is nothing but 54.3 micrometer per second. Okay. Now, capital H is 60 meter. 60 meter whole square divided by log of capital by smaller. Capital R is radius of influence, which is 54.11 meter, divided by smaller is the radius of the oil, which is 0.1 meter. The radius up to which the small h is 0 for maximum discharge. This is nothing but the smaller. And this 54.11 by 0.1 becomes 541. So in the denominator there is log 541. In the numerator 54.83 into 10 to the power minus 6 whole into 3600 becomes 0.1974 meter per second. So meter square into meter per second becomes meter cube per second. Sorry, not meter per second, it becomes meter cube per second. Now, which is nothing but equals to 0.072221 meter cube per second equals to 0.072221 into 60 second, which is nothing but equals to 4.33 meter cube per minute or kiloliter per minute, because LPS means liter per second, LPM means liter per minute. Why is it so? Because it is your 1 minute equals to 60 seconds. So that's why we have converted here meter cube per second to meter cube per minute. Kiloliter means meter cube only. Kiloliter and meter cube. These two units are one and the same. Okay. So till now, whatever I have discussed, nobody has joined. So nobody has any problem. Now we can just go where? We can just go to one problem that was given to our last week's assignment. So people had many confusion on that assignment. So we'll look into that. The solution of that assignment is also shared. If we see that, I mean, the assignment problem was same, only some data was different. Just like in our case, R1 and R2 was 20 meter and 40 meter. Here they are 60, 30 meter, 60 meter. In our problem, the radius of the oil was 10 meter. But here in this case, we can see the radius is, sorry, 0.1 meter. Here it is 0.15 meter. Our capital H is 60 meter, but in this problem, the capital H is 40 meter. In this way, the data are only different, but all the other things are the same. So now we can see the approximate radius of the circle of influence in meters that one has to calculate. Based on that, and the solution sheet has correctly calculated it to be option C 96. In the second problem, that is the problem number 13. Just like our problem, here also they have told to calculate the transmission constant of the aquifer, that is the K, capital K, and after solving they have calculated correctly to be option C 6.4. But when the problem number 14 came, where we have to calculate the maximum rate of discharge, Qmax, they are utilizing the same formula. So Qmax means Q was given as 1500 earlier. Now we have to calculate it in terms of meter cube per minute. So they are capital A squared. They are just applying the Thiem's formula. So capital A squared divided by log of R by R into Km. So Km they have just calculated earlier to be 6.4. So this they have put correctly. Log 10 R by R. So this R will be radius of influence. This R will be the diameter, sorry, radius of the main oil. So it is nothing but 0.0515 meter. All are in meter. This is not in meter though, but yes, it will, after multiplication it will be adjusted. And for capital R, they have calculated 96 meter as the radius of influence or the radius of the cone at the top level, at the water table level. Okay. So this they have correctly identified and put in solving problem number 14 as 96. But you can see this H, capital H square by small square. Small h square is 0 is okay. But this capital H will not be 30 here. You can see from the problem. What is the capital H? Capital H is 40 meter. So if you put it correctly, capital H to be 40 in question number 14, what will happen? The result will be 40 square minus 0, 40 square divided by, that means nothing but 1600, factor is so low. 1600 divided by log of 96 by 0.15 into 6.4. This answer will be liters per minute. If we divide with 1000, then the answer will come as 3.65, 3 point something, 3 point around 3.6 or 3.5, which is nowhere in the options. They have obtained 2.05 meter cube per minute because they have put it wrongly as 30. But this is not a 30. This is 40 in our case. So the answer they are getting here, it is not correct. And we hope either everyone will be given marks or no one will be given marks for this question. So it is basically wrong. The answers, the options those are provided in the questions are wrong. Okay. So whenever you come across in these different these types of problems, we encourage you to have faith on yourself, to be confident enough. If you have watched Dr. Devaputin Pandit's lectures carefully, and if you are doing the problem correctly, if you have revised for 1 or 2 times, then there is no need to worry about regarding what is the option. You can give any random options and you can move on, even if your answer is not there in the options. Okay. So if you are confident enough, if you have watched the lecture well, this type of confusion will not come. Otherwise, you may get confused. So what is the thing? It may so happen that sometimes people do mistakes. So it was a mistake basically. The problem was 2 marks, I guess. Question number 14 was 1.5 marks. So either 1.5 marks will not be given to anyone, or it will be given to whoever have attended, because correct option is not there. Okay. So we'll move on to our promised problem that we have said that we will be solving in this class. So this is the problem based on demand and supply of water. So there is a table in the first column. The type of city is given as cities provided with piped water supply where sewer system is existing. The population of the community is given as 8,000. Sources of water is given as surface water. Characteristics of water to be treated is given as only suspended and bacterial impurities are present inside the water. And number of working hours of the treatment plant is given as 18. Right. Based on this data, the questions are: number one, you have to determine the total water demand. Number two, you have to determine the water to be sent for treatment. And number three, you have to determine the treatment chain with membrane processes. Additionally, you have to decide the number of modules required if flow rate per module is 1 to 20 liters per hour. It is nothing but based on the question number 3 only. It's a subcategory of question number 3. That's all. So now, this is the chart that I showed you today at the beginning of the class. So recommended per capita water supply level for designing schemes is given as: there are three classifications of towns or cities. So number one is towns provided with piped water supply but without sewerage system. For that, recommended maximum water supply level in LPCD unit is 70 LPCD. LPCD means what? Liters per capita per day. Liters per head per day. LPHD it can also be called. Okay. Now, the second category is cities provided with piped water supply where sewerage system is existing or contemplated. There, the recommended maximum water supply level is given as 135 LPCD. Third category is metropolitan and mega cities provided with piped water supply where sewerage system is existing or contemplated. There the maximum water supply level is provided as 150. So you can see, as we are installing, as the cities are getting bigger and bigger, we are installing the piped water supply, or we are basically recycling the sewerage system, right? Then the recommended maximum water supply level also gets increased. If it is even more big, that is metropolitan or mega city, then it is the recommended water supply level is even more based on the demand, right? As we become developed, the recommended level increase. Okay, so now let's focus on the first problem, which has been asked, the rural water demand they are asking. So you can see, just match the type of the city. In our question, the type of the city is given as CPU is provided with piped water supply where sewerage system is existing. So it's existing compared, it is not a mega city or metropolitan city, or it is not a town without sewerage system. It is in the middle. So it is similar to that. Cities provided with piped water supply where sewerage system is existing or comparable. That means 135 liters per capita per day will be the answer for the question number 1. So this is clear. I am just going through. I am not waiting in between for anyone to calculate because nobody has joined. So let's hope it is expected that people will watch the recording later, and whatever question they will get, they will post it in the discussion forum, and accordingly we will address the questions. Okay. So now let's dive deep into the question number 2, which is water to be sent for treatment. Okay. So to calculate the water to be sent for treatment, we have to get the total water demand in liter per day. So to get the total water demand in liter per day, we have to multiply the population of the community with the per capita demand, which is nothing but 135 liters per capita per day into 8,000 number of populations that we have just calculated respectively, which after multiplication comes out to be 10 lakhs and 80,000 liters per day, right? Yeah, it's 10 lakhs 80,000 liter per day, right? Now we will move on to our next problem. So this we have calculated as 10 lakh 80,000 just per day, we will just again look into the membrane process characteristics in order to get the solution of the problem number 3, which is asking treatment trend with membrane processes. So to determine the treatment trend with membrane processes, we have to look into the characteristics of water that is to be treated. So we can see that only suspended solids and bacterial impurities are present inside the water. So to calculate, we have to tally the earlier membrane chart that we just studied in our last class. So only suspended solid and bacterial impurities are present. That means the ultrafiltration, nanofiltration, reverse osmosis are not required because viruses are not present. Multivalent, monovalent ions, they are not telling that you have to separate them. So that means only bacteria and subsolids, if you have to separate, microfiltration will be sufficient. Why not ultrafiltration, nanofiltration, and arrow? They also separate. We will come into that in a later stage. So yes, the earlier problem was 10 lakh 80,000 liters per day. Yes. So here the source water contains suspended and bacterial impurities only. Hence microfiltration membrane treatment scheme will be sufficient. Now let's ask again that question. So the ultrafiltration, nanofiltration, reverse osmosis, they are also able to separate bacteria suspended solids, right? So why microfiltration and not the other? It is because the microfiltration requires the least amount of pressure among all the other membrane processes. Okay, so if there is the high pressure requirement, then the energy requirement will be more. Subsequently, the electricity bill that the plant has to bear with will be more. That's why to reduce the operation, to minimize the operational cost, microfiltration will be sufficient. There will be no need of ultrafiltration, nanofiltration, or RO. You have okay, why that it is clear. So now it will be MM skin, that means the microfiltration skin. Now we have to decide the number of modules required. If the flow rate per module is 120 liters per hour. So data is provided, flow rate per module is 120 liters per hour. This data is provided. Water to be treated by a single module within the total working hours, which is 18 hours given in our question, will be, so 100 liters per hour is given. 18 hours, if we multiply it, it will be 2106 liters, right? So this is the amount of water that this is the daily number of working hours. So this is the amount of or volume of water that needs to be passed through the membrane per day. Okay, so the actual 24 hours demand needs to be met within the 18 hours time only. So whatever the demand is there, water demand that we have calculated, this 135 liters per capita per day or 10 lakhs and 80,000 liters per day, this demand, this is the demand for 24 hours, because whenever the plant is not running, it is not like that the people are not using water. People are using water that time. Maybe the plant is running under two shifts, two shifts of 9 hours each, but with a gap of 1 hour in between maybe. But it is not like that the other 7 hours people are not 7 hours, 6 hours. It is not like that for the other 6 hours people are not using water. It is not like that. So this liter per day, this is the water that people are using throughout the day, or this is the demand maximum usage. But you have to be ready for the maximum supply of water to meet the maximum demand. For that reason, you have to design the plant in such a way, because you are operating the plant for 18 hours, you have to, maybe you can build a intermediate storage facility for where the water will be stored for use for maximum usage purpose. Again, later day when the shift start, you will again start the pump. But here you can see that 18 hours of working hours of the treatment plant is meeting the 24 hours demand. That means total number of membrane modules that will be required is nothing but 10 lakhs and 80,000 liters per day divided by 2160 liters, because this is the uh, this is the what flow per module is 120 liter. So 2160 liters is the volume of the water that should be passed through one single module in a day, and this is the total water treated in a day. So water that needs to be treated maximum in a day. So that means total amount of water divided by per module passage gives you the number of modules, right? So it is nothing but 10 lakhs 80,000 liters per day divided by 2,160 liters. It is nothing but 500 number of modules. If we consider 5% standby, then the total module number of modules will be required as 525. We have already discussed what is the concept of standby. In case of, for example, here it is shown, it is the conventional stacked RO module for desalination plant. In desalination plant, if let's say there are two pumps, if one pump is currently running or in operation and it gets damaged, then there is isolation valve at the discharge sides that you have to discharge or suction side, both sides it may be there. You have to close that valve. Somebody joined, I think. Let's see who joined. Okay, non. Let me pause the recording for some. Resume the recording. So now, okay. So I have already explained the concept of standby. So if one pump is in operation and it gets damaged, then the plant should not be stopped for continuous operation. Then we can basically keep one pump isolated from the circuit and run the other pump in order to maintain the operation of the plant. All right. So that is the thing here. Now we have solved all the four problems: the total water demand, the water that sent to be that needs to be sent for treatment, and treatment 10 with membrane processes. So now, and also if considering the standby module, what will be the number of the modules? That is 525. Now there is buy one get one free. One more problem, that is problem number 5. If one microfiltration train contains 25 modules, then we have to calculate the number of MF trains required. Okay, so basically,
AI will not replace programmers, but programmers who use AI.
explain what is the membrane train. Basically, there are two types of membrane operation that is possible. One is in parallel and one is in series. So whenever we use series operation, that is for more and more recovery. Let's say we have placed one RO parallel to another RO. That is because the flow rate is more, and we have to cater the amount of the flow rate by spacing more amounts of modules in parallel to each other. But what is the function of the function of placing the module in series? That is to get more and more recovery. That is the idea here. So that's why basically the more if there are three stages, that means one train should contain 3 stages. If there are 2 stages, then one train will contain 2 stages, like that way. One train may contain one single stage also, if we don't require further recovery. Sometimes the permeate that is coming out of the plant, that is our focus. Sometimes what happens, sometimes the permeate and sometimes the retentate or concentrate that is coming out of the plant, that is our focus, which is basically the case of fruit juice concentration. Yes. So now in this question we have asked about, what is this? Yes. So there we have asked about, if one membrane train contains 25 modules, we have to calculate the number of membrane trains. Membrane means here it is the microfiltration membrane or MF trains. Previously we have calculated 525 is the required number of modules. If the flow rate per module is 125 liters per hour, that means if one membrane train contains 25 modules, it is simply 525 divided by 25 equals to 21 is the required number of modules. So one train will be in standby mode, the other 20 modules will be in operational mode. So what are the main membrane problems we face? That is basically your fouling and selectivity permeability trade-off. For that reason, we need to clean the membranes. So if we cleaning one train, then we can keep the standby train in operation. This is the idea. Okay. So what is the time now? It's 8:44. We can run for 15 minutes more. It is up to 9 p.m. So I will go through some other MCQs. The first one is the economic water scarcity. What is it? So if there is people who creates the demand of water and there is the source of supply of water, if even if there is sufficient source, if the management or infrastructure for distributing the water from the source to the demand side, that is the people, is not sufficient, then one artificial scarcity of water may occur. This is basically the man-made water scarcity. Water source is there, demand is there, but scarcity is occurring due to the insufficient or inefficient management infrastructure or ineffective management infrastructures, which is not distributing the water properly from the source to the people. So this is something called as the economic water scarcity. So we will solve a problem based on the demand and supply of water. So a lake in Bhopal having approximate volume of 5 into 10 to the power 11 meter cube with an average annual outflow of 0.7 into 10 to the power 10 meter cube per year. So calculate the HRT, that is hydraulic retention time, for the lake to the nearest integer. Option A is 70 years, option B is 72 years, option C is 74 years, and option D is 76 years. So as no one is there, so I will not wait for the solution of the problem. I'll just go through the detailed explanation. To solve the problem, one concept is required, which is called as the hydraulic retention time. Let's say there is a completely mixed tank, which is sometimes called as the constant start tank, CST, through which liquid is flowing. So there is one flow in stream and another one is flow out stream. Now, under steady state condition, steady state means what? Where flow in equals to flow out. That means the height of the tank, height of the water inside the tank is not changing if the incoming flow rate is equal to the outgoing flow rate. In that case, HRT or hydraulic retention time will be equals to the tank volume divided by the outflow, which is nothing but equals to the flow in. If there is mass or solids present inside the tank, then another concept is there, that is called SRT, or solids retention time, which is nothing but equals to mass of solids inside the tank divided by mass of solids leaving. This is called as the SRT, or solids retention time. But in our case, only the HRT, or hydraulic retention time, will be required. For our lake case, we can assume the lake in Bhopal as a completely mixed tank, where residence time is the average duration of a particle of water to pass through a phase of hydrological cycle. Thus, the HRT, or hydraulic retention time, in our case will be the volume of the tank or lake, which is nothing but 5 into 10 to the power 11 meter cube, divided by the annual outflow, which is 0.7 into 10 to the power 10 meter cube per year. That is nothing but equals to 71.43 years. This is the retention time of the lake. Okay. So option B, 72 years, is the correct option in our case. Okay. So now let's move on to our next MCQ, which is a multiple choice question. One option will be correct. The rate of reaction depends on which one of the following? Option A is products, option B reactants, option C both products and reactants, and option D is none of them. So the correct answer is both products and reactants, upon which the rate of the reaction depends. It may be a first order, it may be a second order, or it may give some feedback for a negative order reaction also. That means the concentration is increasing and the rate of the reaction is decreasing. It may also happen. So both products and reactants are responsible for the rate of the reaction. Now next MCQ is the ratio of the quantity of water retained by the material against gravity drainage to the total volume of the material of subsoil is defined as. Option A is porosity, option B is specific yield, option C is specific retention, and option D is permeability. Okay, so here the detailed explanation is something like this. Specific retention or field capacity of the soil is the ratio of the quantity of water retained by the material against gravity drainage to the total volume of the material of subsoil strata. That means specific retention is the correct answer in our case. So now next MCQ is, which one of the below are toxic natural constituents in water? Option A is sodium, option B arsenic, option C sulfate, and option D nitrate. Detailed explanation is As or arsenic and F or fluoride are natural constituents and are toxic in nature. The arsenic or As can cause skin cancers, gangrenes, and or other diseases. Hence, the arsenic is the correct answer. Okay. So now the next MCQ is, the characteristics of fresh and septic sewage respectively are alkaline and acidic, acidic and alkaline, both acidic, both alkaline. So the explanation is something like this. The pH, that is the concentration of the hydrogen plus ion of fresh sewage, is more than 7. The average range is in between 7.5 and 9.5, and hence fresh sewage is alkaline in nature. Now we know that in septic tank the sewage remains for certain time, so that's why there are bacteria, there are acidophilic and bacteria, and there are also anoxic bacteria which basically degrades the sewage material. That's why the pH becomes acidic, that is less than 7. In case of septic sewage, it is in the range of 6.5 and 4.5. Hence, the septic sewage is acidic. So, option A is the correct answer in our case. So, the next MCQ is, which one of the following factors doesn't affect the rate of the sewage load? Option A is rate of water supply. Option B is population growth. Option C is infiltration of groundwater, and option D is design of sewer system. So option D is the correct answer, design of sewer system. Why the other answers are not correct? Because rate of water supply will increase the sewage load. Because within the sewage treatment plant, the inflow consists not only the sewage that is coming with the water. If the water increases, the inflow increases. That means the load increases, but the concentration of sewage that is the present in the water may vary. But as the rate increases, it increases because of certain purpose only. So that's why the sewage amount increases. The population growth is definitely increases the amount of the sewage growth. If the infiltration of groundwater happens, then the concentration of sewage that is present uh, inside the inflow of the sewage treatment plant, that may get reduced. So all these three factors affects the rate of the sewage growth. But design of the sewer system is something which is done at the very beginning, before the commissioning of the treatment plant, before, even before the construction. So that's why this basically doesn't affect the sewage load during operation. This is the correct answer in our case. So now next MCQ is, non-spherical particles will settle slower than, faster than, equal to, or same as the spherical particles. Which is the correct answer? So slower than is the correct option, because there is one concept that is called as the sphericity, which uh, which is nothing but the ratio which compares the specific surface area of spherical particle and the non-spherical particle. Why it is done, this sphericity thing? It is done to calculate one velocity that is termed as the terminal settling velocity. When the drag of the water, drag is represented as Ft equals to 6 pi mu RV, or 3 pi mu dV, where V is the terminal settling velocity and Ft is the drag force. If you equate these two terms, then you will get the terminal settling velocity. So if the terminal settling velocity of the of spherical particle is basically the mode. Why? Because in case of spherical particle, the sphericity is 1. That means the drag force is lowest in case of spherical particle, but the drag force when the particle is moving through the water, it is highest in case of, as the curvature of the surface area increases, then the drag force also gets increased, the projected area. So that means the spherical particles faster spherical particle settles faster than the non-spherical particles. That means these non-spherical particles settle slower than the spherical particle. Option A is the correct answer. Now, next MCQ is, the peak factor is given by option A, peak flow into average flow, option B, peak flow minus average flow, option C, peak flow plus average flow, and option D is peak flow divided by average flow. So it is nothing but a memory based question. Peak flow divided by average flow is the peak factor. Whenever the factor comes into the picture, it is something with which we want to multiply something to get one answer. So that's why the ratio will be the answer in most of the cases whenever the factor is asked, because we want to multiply something with this factor, so that denominator will get cancelled out like that way. So now the next MCQ is, For a given discharge, the efficiency of the sedimentation tank can be increased by option A is increasing the depth of the tank, option B decreasing the depth of the tank, option C increasing the surface area of the tank, and option D is decreasing the surface area of the tank. The discharge is fixed. Now, how can we increase the efficiency of the sedimentation tank? So option C is the correct answer. If we increase the surface area of the tank, because surface area is something which reduces the velocity of the incoming water. If there is a sudden drop in velocity, then the settling will be more. So if we increase the surface area of the tank, then the drop of the velocity, that means the delta V, that will be more, thereby increasing the sedimentation inside the tank. Okay. So now, uh, let's see what is the time. Yeah. Okay. So the grid chamber can be covered, I guess. Okay. So grid chamber is something which also separates particles that is present inside the water. It is basically purifies the water. The inlet water flow comes in. Fats, oils, and grease, which has lower density than the water, it actually floats on the surface. That can be taken out separately. The grids, which is the mainly separated inside the grid chamber, that is settled at the bottom with the help of the compressed air. So compressed air is passed from the bottom to top. So that is a counter current operation. Water comes from top to bottom and compressed air goes from bottom to top. And the fresh water is taken from the outlet. After certain amount of time, if there is sufficient grit that is present inside the water, or the grit is coming above the compressed air, the pressure drop will be more. The energy consumed by the compressors, that is pressing the compressed air inside the grit chamber, the energy consumption will be more. In this way, you can understand that there is sufficient amount of grit that is stored at the bottom of the grit chamber. Then we can just stop the operation for the time being, or if there is one parallel grid chamber that is present along with this grid chamber, we can keep that in operation and isolate this from the system, and we can take out from the grid from the bottom shoot. Okay, so now this is the concept of grid chamber. There is one problem based on the grid chamber. I hope we can solve that in later class. So let's conclude this class here only. So we can, it is 9 p.m. So we will solve the problem that is based on the grid chamber in the other class. In the next class, that is your next Sunday. Today is 18th and next Sunday is 25th from 7 to 9 p.m. We will again meet to solve the problem of the grid chamber. Okay. So today up to this only. I will stop the recording. Okay. Good night.